Welcome to the first video recording for the 5th class section in our series of video recordings of these lecture notes. We're going to be switching gears from atomic theory to actually representing organic molecules, and then a little bit of naming as well, and eventually we will transition to conformations of organic molecules. So, for representing organic molecules, I'm sure students are probably familiar with the condensed formula if they've been keeping up with assigned or recommended practice problems in the book. For example, here we have ethanol in its condensed formula. You might read it from left to right as CH3CH2OH. A calculae drawing of the ethanol structure would kind of look like a flattened out structure where each carbon has 4 straight line bonds. This terminal carbon on the left has 3 straight line bonds to hydrogen atoms, and then 1 straight line bond to the adjoining carbon atom, which has 2 straight line bonds to hydrogen atoms and 1 straight line bond to an oxygen atom, which has a second straight line bond to a hydrogen atom. Of course, the type of structure we will see most frequently in this class will be bond line, and it's perhaps the most convenient way of drawing an organic molecule. Each point represents a carbon atom, so this is the terminal carbon atom on the left. We assume that students know that carbon should be bonded to 4 different things, so these bonds that are not explicitly drawn on this carbon atom on the very left must be to hydrogen atoms, and there must be 3 of them. Similarly, this vertex, this point, is a carbon atom, and one would assume that it has 2 hydrogen atoms bonded to it because it has 1 bond to an oxygen on the right and 1 bond to the other carbon on the left, so it has remaining 2 bonds that must be satisfied. So in the bond line representation, we assume those bonds are to hydrogen atoms, and of course we've drawn out an oxygen and we've explicitly put the hydrogen on it. Typically when we draw non-carbon atoms, we explicitly write how many hydrogens are associated with them in our bond line structures. So another example would be dimethyl ether. So here we have CH3O, CH3. Sometimes you might see condensed formulas where the hydrogens are written to the left of the carbon, so H3C, O, CH3. That's perfectly valid as well. The calculae structure has everything drawn out explicitly, and then the bond line structure is perhaps the easiest representation for this molecule in shorthand. So, both ethanol and dimethyl ether have the same empirical formula of C2H6O, but they are very different molecules as we've represented them with very different physical properties. You could call ethanol and dimethyl ether constitutional isomers. Those are molecules that possess the same formula but have a different connectivity of atoms. So hopefully by this point we're getting used to my cursive writing. We'll go ahead and go through a few more examples for this representation of organic molecules in condensed formula, calculae, and bond line. Some more examples. Here we have hexane, cyclohexane in fact, where we've got CH2 parentheses and 6 of them. So they happen to be connected. We could draw out a calculae structure which is very tedious, showing all the carbon atoms explicitly bonded in a ring to each other, and then each carbon atom bonded to 2 hydrogens. The bond line diagram's much simpler. It's simply a cyclohexagon or a hexagon. Another way you might see cyclohexane is in this conformation, which is a chair form. It's not like the bond line in that we've sort of twisted our cyclohexane molecule and we are viewing it out of the plane of the page. So it looks sort of like a lounge chair. We'll return to this and talk about it at length in our chapter on conformations. How about this interesting molecule, H2CCH, C parentheses O, CH3? Well, for our condensed formula, we kind of suspect some interesting bonding is going on between our leftmost terminal carbon and this interior carbon. Additionally, this interior carbon with right next to an oxygen parentheses is indicative of some higher order bonding than just single bonds. And so when we diagram out our molecule in the Kekulé structure, we see, oh, there is a double bond between this carbon and this interior one. And then our carbon next to the oxygen parentheses has a double bond to that oxygen. In bond line, we could represent this molecule like this. Don't be fooled by free rotation. This is another perfectly valid representation of the same molecule. We've just twisted around this carbon-carbon bond such that instead of having the hydrogen atom here that's not explicitly drawn pointing straight up, we have the double bonded carbon pointing straight up, and now the hydrogen atom that's not explicitly drawn is pointing down and to the left in the plane of the page. If these are difficult, I'm sure we'll have a chance to practice them in class. Here's an interesting example where our condensed formula shows a cation. We've got H3C, CCCH2, NH3+, and so the plus is actually associated with the nitrogen. We can see that explicitly when we've drawn out our Kekulé structure. We also see, oh, there's a carbon-carbon triple bond for these two carbons that don't appear to have any hydrogen atoms associated with them. That's because they have a triple bond between them, and then their other bonds are two carbon atoms in the molecule. It's kind of strange when we draw out the bond line structure because we're used to seeing carbon in our bond line structures possessing some sort of vertex in terms of its bonding, but we have to remember that for the carbons involved in the carbon triple bond carbon, those possess a linear geometry because they're sp hybridized. And so we have to be mindful that there are actually 1, 2, 3, 4 carbons in this bond line structure. Occasionally you might see in catalogs that carbon triple bonds are still represented with a vertex, just to remind you that there are carbon atoms here and there. So one last set of examples and that will be it for this video. So in our final set of examples we have a condensed formula of H3CCClBrCH3. We could draw a Kekulé structure as follows, where we put both the chlorine and the bromine on the central carbon in this molecule. Our bond line carbon has now the 3 carbons in the plane of the page, with the bromine atom possessing a wedge in this representation and the chlorine atom possessing the dashed bond. We could draw a axis going straight through the middle carbon and then flip the molecule around 180 degrees. And if we did that, we'd still have the carbon's backbone in the plane of the page, but now our chlorine atom would possess the wedged bond and our bromine would possess the dashed bond. And these are the same molecules. How do I know they're the same? Well, I could simply do that procedure again, draw an axis, a vertical axis going through the central carbon, flip it around 180 degrees, and then everything superimposes. So we'll have to be, or get used to, performing those sorts of operations in our heads and on paper. Note, the wedged bond and the dashed bonds go on the convex side of the bond line diagram and never on the concave side for the purposes of our class. So what do I mean? I mean the wedged and dashed bonds go on the side that has the greater angle. You can't just put one on the side that has the greater angle and the other on the concave side, which has the smaller angle, because it would be difficult for an organic chemist to tell, especially when we get to the topic of stereocenters, what representation that molecule actually has. And we'll see that when we hit that chapter. But enough for this video. I'll see you in the next recording.